Hi, and welcome to week 6 of Intro to Physics. I'm Claire Blackman. I joined MSP in January, so I'm quite new. And this week we're going to be looking at vibrations and waves. So just to recap everything that you've seen so far, and you've seen a lot. In week 1, you looked at classical mechanics, which takes a fairly simple view of everyday physics that we use to understand how things move, things like cars, planes, when you walk, what happens, things like that. Week 2, you had a look at astrophysics, which takes a kind of even broader view of the universe, so trying to understand the physics of the universe. And then electromagnetism, which is understanding things like how light propagates, electricity, magnetics, things like that. Then you had a quick look at thermodynamics, which is talking all about heat and aspects of describing the world from that perspective. And then finally last week you got to look at quantum mechanics, which is really looking at how the world behaves on a very small scale. So far you've had an overview of 5 different ways of looking at the world and the kind of the physics or the mathematics that we can use to model those views of the world. So what are we doing this week? Well, the thing is that there are certain phenomena that we observe no matter which branch of physics we're looking in. For example, if we look at bridges or pendulums or cars, so we're looking at the classical mechanics kind of view, we're going to see that there are vibrations and waves. So earlier this year, you might have seen some newspaper headlines about a skyscraper in China that everyone had to evacuate because it was oscillating from side to side. Some years ago, there was a famous bridge called the Tacoma Narrows Bridge, which started oscillating in the really unnerving way that you can see in the image here, and eventually collapsed. So there's vibrations happening in everyday life. But if you go to astronomy and astrophysics, then you will also see that things vibrate, that there are waves. So there are many stars where if you measure their brightness over time, you'll see that they change periodically. And there are many different reasons for that. And in fact, there are different explanations. One kind of star, in fact, brightens and dims depending on where you are on the star. So that's the image that you can see on the right here, the different bands of oscillations of brightness in stars. So there's brightness fluctuations all over the universe. And in fact, when you studied electromagnetism, you would probably have realized that in fact all of electromagnetism is all about waves. It's about light waves and about photons. Photons oscillate, everything oscillates. So electromagnetism really is all about waves. You can also have a look at thermodynamics. Now thermodynamics is all about things moving, about heat, and in fact if you look at molecules, there are many different ways in which molecules can oscillate. And finally, if we get to quantum mechanics, you just did a tutorial on tunneling. Well, tunneling is modeled using waves as well. So we have this kind of phenomenon that occurs on all different levels, which is that things oscillate. So that's really what we're talking a little bit about this week, is to just give an overview of how we can mathematize and think about things which kind of change periodically. So in order to do that, let's try and think a little bit more about exactly what it is that we're trying to describe here. So let's start by thinking about a vibration. So I went to good old Wikipedia and pulled out their definition. And they said that vibration is a mechanical phenomenon whereby oscillations occur about an equilibrium point. I quite like the fact that it comes from the Latin word for shaking or brandishing, so that gives you a very vivid idea of what's happening. We're shaking, we're brandishing things. And Wikipedia adds a little bit more. Our oscillations can be periodic, so if we're thinking of things like pendulum or random. Okay, so that's helpful. You'll see that I've crossed out mechanical because vibration doesn't really have to be mechanical. It can be any kind of phenomenon which has oscillations. But the thing that we do need to think a little bit about is, okay, what do we mean by oscillations? What do we mean by equilibrium? What do we mean by periodic? And we could think about random as well, but we're not actually going to do that for today. So let's clarify that. What do I mean by an oscillation? So the key thing about an oscillation is that it's a repetitive variation. Usually we're thinking about oscillations in time, so something that is changing repetitively over time. And the other kind of key idea here, which is going to bring us to our next word, is that it's an oscillation around a particular point. So either above and then below and above and below, and we call that particular point the equilibrium. You can also have a situation where you are oscillating between two states. So for example, if you think about the power station that you did in one of the tutorials, you could think of an oscillation for the water, well, for the H2O, that was going from liquid into steam and then going back into liquid, back into steam. So it's an oscillation between 2 points. But for most of what we're going to be talking about today, we're just thinking about something moving in a periodic motion over time. Okay, so we've said equilibrium. Let's define that a little bit. Well, we're just going to call an equilibrium the condition of a system in which all competing influences are balanced. So we think of something, we say that something's in equilibrium if it's stable, it's not moving. For example, all the forces are balanced. So we just have a system where everything is balanced. There's nothing that's going to cause it to move if it's not already moving. So you might have something that's already moving, but so you're not getting any acceleration, anything like that. It's a little bit of a hand-wavy definition, but hopefully that will be good enough. Okay, 2 more words that we want to think about. What do we mean by periodic? Well, periodic, we mean the motion repeats itself over and over again. So you get the same thing happening again and again. And linked to that, we haven't seen frequency yet, but I just wanted to put it in here. We have that frequency is the number of occurrences of the repeating event per unit of time. So you have, if something is periodic, it's going to be repeating, and you count up how many times it repeats, for example, in a second, and that's going to give you your frequency. Okay, so there are the words and the kind of ideas that we're going to be using today. So how do physicists go about studying periodic phenomena? Well, we have a basic, simple system that we look at as our very first example of periodic phenomena. And then from this very simple system, which we're going to call simple harmonic motion, we can extend these ideas to kind of deal with periodic phenomena of all sorts. So what we're looking at for the first part of this lecture is just how do we describe things like a simple mass bobbing on the end of a string. And there are 2 kind of competing ways, depending on which university you go to, which one you're going to look at. You might look at a mass that's bobbing up and down, like you can see on the left here, or you might think about a mass moving on a table with no friction according to a spring. And that's the one that we've got on the right, and that's the view that we're going to look at, mainly because it actually fits better on the screen. If we were in the lecture venue, I might actually choose to show you something bobbing up and down, but yeah, for today we're going to think about that. So you'll notice that in both of these situations here, whether we're going up and down, there is the equilibrium point. So if you imagine that you just took your mass and you just let it hang from the spring, you didn't cause it to bob at all, there would be a certain point that it hung at, and that's the equilibrium point. Similarly, for the mass on the right, if you just kind of left it to quiet and down and stop moving, there would be an equilibrium point around which it wouldn't move. But as soon as you perturb either of these, so you pull on the spring to start the motion, then you see that the motion moves either side of the equilibrium point. And you'll see that this has all the features of what we've talked about in a vibration. So it's got an oscillation, so it's got a periodic motion on either side of an equilibrium. Okay, so this is the picture that we're working with, the mental model, and now what we want to do is we want to develop the mathematics for that. So I'm going to switch over to my iPad from my shiny PowerPoint presentation so that I can actually do a little bit of writing. Okay, so what do? Well, we look at our system and we think about the things that we can notice about it. So there are first 2 things to notice about our very simple mass spring system. The spring is always going to apply a force towards the equilibrium position. So it's often called a restoring force because it's always pulling the mass back towards equilibrium. So the system is trying to return to equilibrium, it's trying to return to stability, and the force is doing that. And the second thing that we're going to notice is that the restoring force is proportional to the distance from the equilibrium. So let's look at those 2 ideas a little bit more deeply. So here I've got some pictures of our mass spring system in 3 different states. So we're imagining that it's moving, and we've just taken 3 snapshots. in the first image over here, our spring is compressed. And if you think about what's happening when you've compressed the spring a little bit, we're going to have the force of the spring is going to push the mass towards the equilibrium point. So you imagine you've compressed a spring, it is pushing outwards, it wants things to move. I'm going to skip to the third image over here. So now our spring has been stretched out, and if you imagine when you pull a spring, then it wants to compress back together. So if you think about what would be happening to our mass over here, in this situation, the force on the spring would be pulling it back towards the equilibrium. At the equilibrium point, the spring is at its kind of equilibrium quiet value, so we don't actually have a force acting. But because we will have a little bit of motion left over from the spring, the mass moving to the equilibrium, it's going to move past, and then whichever side it's on, it's going to have a restoring force. Okay, so the key thing here is we have a force that changes direction. It can be to the left or to the right, depending on where the mass is, but the force is always going to point towards the equilibrium position. So that is one of the key features of simple harmonic motion. You have a restoring force that's always pushing the system towards equilibrium. So the other thing that we can notice about this, we can actually talk a little bit about how big is the force. So the force must change over time because, well, we know that it changes direction, so we kind of assume that somehow it's changing from being kind of really strong in one direction, getting less and less and less, then it changes direction and now suddenly it's less and less, and then it gets bigger. So we have a force, and in fact our restoring force is roughly proportional to the distance from equilibrium. What are we saying? Well, if we're looking, here's our equilibrium point over here. We know that in this situation our force is going to be pushing towards the equilibrium, but we can actually go a little bit further and we can say, well, if x is our distance from our equilibrium point, then our force is going to be proportional to that distance. So if you think about this in terms of the intuition that you have with springs, if we'd really compressed this so that our mass was over here, so quite far away, if you think about it, you'd have a very compressed spring and the force it would be exerting would be really big. So it would be much bigger than if our mass was just over here, so our spring wasn't really compressed at all. So we have a situation where our force is changing over time, and the way it changes is proportional to the distance from equilibrium. We'd have the same thing happening in our situation over here. So here we know that our spring force is now in the opposite direction to what we just discussed, but again, if we measure this distance here, then our force is going to be proportional to that distance, approximately. And I'm going to talk about why I'm saying approximately in a moment, but we just want to get the intuition here. And again, if you imagine, if you'd really stretch this spring out, the force it exerts to kind of pull back to equilibrium is much stronger than if you just pull the spring a little bit apart. And over here, well, we know that there's no force acting on our little mass when it's going exactly through the equilibrium point, and that kind of works as well. We still have that our force is proportional to x, but here, because we haven't moved from our equilibrium, so we're measuring x as the distance from equilibrium, our displacement is 0. So our force is proportional to 0, so it must be 0. Okay, so these are the two ideas that we take into how we model this mathematically. So we've talked about forces, and from the first week, you know that pretty much anything we do when we're thinking about things in this context, so we're starting this out in the classical mechanics modeling way, is we look at the force diagram, what's happening here. So let's just do a quick check of that. Well, let's look at our first situation. So we've compressed the spring a bit. What are the forces acting on our mass? Well, we always have gravity acting down. We are not having our little mass disappear into the table, so we must have an equal but opposite force, so that's going to be our normal force, and those two balance each other out. And then for the purposes of what we're talking about, we don't have any friction. So the only force that we have is the force of the spring on the mass in the horizontal direction. So that's our force from the spring. In real life, you would expect that you might have a frictional force going in the opposite direction, but we're just kind of doing an idealized, as simple as possible experiment here, so we don't have that one. We just have, in the horizontal direction, we only have the force due to the spring. Okay, so if we look at our next situation over here, now when our little mass is at equilibrium, the only forces acting on it are gravity, so we have our gravity going down and our equal and opposite normal force going up. And then we can play the same game when we look at our final situation over here. And now, again, we've got gravity, we've got our normal force, and we've got our force that is now restoring in the opposite direction. So we've got our spring force looking like that. So we've already talked a little bit about our restoring force, and the key thing to take out of these three diagrams is that our motion isn't affected by gravity, because we're ignoring friction. So in fact, all we really need to think about is what's happening in our x direction, in our horizontal direction. So for the rest of this, we're going to ignore gravity and our normal force and just look at that force that's acting due to the spring. Okay, so what can we say about this force? Well, we've said that it's approximately equal, it's approximately proportional to the distance. In fact, if you were to kind of do this thoroughly, you would find that the force due to the spring can be written like this. So there's a lot of terms here. Let's have a look at what's going on. So we put the negative sign in because we're assuming that we have x increasing to the right, which means that if x is increasing in that direction, then our force will be in the opposite direction. Whereas if x goes to the negative, so let's put our 0 there, if we're looking at some x over here, which is a negative x, then we want our force to be in the opposite direction, which will make it positive, so then our first force will be going in that direction. Okay, so that's why we've got a negative over here. This term is the one that we've said in our approximately proportional to, because remember, if you have a force is proportional to x, then what that really means is that there's some constant so that which you multiply by to get your force. You multiply your displacement by to get your force. So that's this term. What are all these other terms doing? Well, I'm going to refer you to go and have a look at a Taylor expansion if you're curious. If you're not curious, don't worry about it, just trust me. There are terms that depend on the square of the distance and the cube of the distance and so on. And you might initially look at this and go, well, that's not good because we know that x squared is bigger than x. So why am I saying we can approximate our force just using this term? Well, the key here is that we're going to be using very small distances. So we're going to be looking at little distances that we can measure that are much less than 1. So I'm just thinking of the size of the displacement that we're looking at. They're going to be very small, much less than 1. And you know that if you square something very small, you get something even smaller. So what essentially happens is that these terms become negligible and we can ignore them. So what we've got is we've got very small displacements that we're thinking about, and this means that x squared, x3, and so on the thing to notice here is that we are assuming that our equilibrium point is where x is equal to 0. You can do this by taking x equals 0 somewhere else, just makes things a little more complicated. Let's put this into a diagram and think about exactly what's happening, and make sure that it does give us the right answer. Okay, so we are saying that x equals 0 is at our equilibrium point. So do we get the right forces? Well, if we've got that x is equal to 0 over here at this point, and we've compacted down our spring. So now our actual x measurement is less than 0. It's a negative number. What will we get? Well, we get fs of x, fx is equal to, now if we are assuming that our k's are all positive, then we would get minus k1 times something negative. Because our x is less than 0, and so we've got something negative, we've got a negative over here, so our force from our spring here is going to be positive. And that's what we expect. We want it to be in the positive direction. On the other hand, if we look at our situation where we're in equilibrium over here, well, looking at this expression up here, what's going to happen? Well, our displacement, our x is 0, so when we plug in x equals 0, in each of these cases over here we get 0, and we're adding together a whole bunch of zeros, so our force is 0. So far it looks like this model is working. Let's just check it for our final case over here. For our final case here, the x that we put in will be greater than 0, and if we think about putting that into our equation up here, we would get a positive number going in here, so this term would overall be negative, which gives us our restoring force pointing back in the negative direction, back towards equilibrium. So it's working. A couple of things to notice. If you were to include what we call higher order terms, so these are our higher order terms, what would happen? Well, remember we're talking about very little measurements, so x squared, no matter which side we're on, whether we're on this side of equilibrium or this side of equilibrium, x squared is always going to be positive. So this term is always going to be positive, but don't forget there's a minus sign multiplying in there. So this term over here tends to subtract off a little bit from your restoring force, whichever side you're on. So if we were on this side over here, where we're getting a positive restoring force, if you included your second order term, your x squared term, it would be slightly smaller. And if you were on this side over here, you'd be subtracting off something, so it would be subtracting, so we know that we've got a negative restoring force, and we'd be subtracting for a little bit more, so it would make that a little bit bigger. So it just makes little changes, but not a lot. And you could think about what would happen if you included a third order term, but for what we're doing, we don't need to. So what I've just been saying here, we can always pick a small enough x. So again, I'm saying that the absolute value of x is a lot less than 1, so that if I square it or I take its cube, it's so small that I can just ignore that. We're also assuming that our k's, so our k2 and our k3, are quite small as well. But the important one is always going to be k1. So where does that take us? Well, if we're ignoring all those higher order terms, really we can take this crazy long thing over here and we can turn it into something that you've probably seen before, which is Hooke's law. So Hooke's law is an approximation, and you've probably heard it said that you can only use Hooke's law if you're not going to kind of expand your spring way further than it should, which makes sense because you know that if you expanded a spring way further than you should, it might stop being springy, or it might even snap. So clearly at that point, Hooke's law isn't going to work. But if you have a spring and you're just doing little changes, Hooke's law works well. Okay, so this, in fact, is the model that we're going to use for our spring law, and we've seen that it makes sense. So it tells us that depending how far we are from equilibrium, we will have a bigger or smaller force, possibly a zero force, and also the force will change direction. Okay, so Hooke's law tells us a lot about how we're modeling this system. That's nice. Now we have an expression, a mathematical expression for the force. How can we use that to model the system? Well, don't forget, very important, our classical mechanics f equals ma always still true. So we know if we're modeling in the x direction that we must still have that this law holds. So we have that f equals ma. So specifically we must have that the force exerted by the spring must be equal to our mass times by its acceleration. Okay, so that's pretty nice. Can we combine these two? Absolutely. So we know from our previous slide that our spring, the force due to the spring, is some constant times the displacement. So we have two equations. Let's combine them because we've only got this force acting in the x direction. So here we go. So we've got m d squared x by dt squared must be equal to minus k1x. How does this help us? Well, I'm going to divide through by m, so I get minus k1 over mx. And if you did the maths for this section, you would see that, well, both of these are differential equations. And there's a whole bunch of mathematics around how to solve those. What I'm going to do in order to solve this is make one little substitution. So I'm going to let omega squared be k1 over m. It's not entirely clear why I'm doing this crazy thing right now, but you're going to see when we solve it why it's useful to do this. So if I do that, then I end up with a differential equation that says that the second derivative of my displacement, so my acceleration, must be equal to minus omega squared times whatever my displacement is at that particular time. Okay, so that's a differential equation. And we need to solve it. So remember what we're trying to do. We're trying to find some function which describes our displacement over time. So we'd like x of t is equal to some function of t. Because if we have that function of t, then we can say, well, okay, I want to know where my system is at time t equals 20. I can plug t equals 20 into this equation over here, and it will tell me what the displacement is. So we'll be able to model where our little mass is at any given time. So that's where we're headed. So we're trying to find this function. Now, there's a whole course that you can do on solving differential equations, and you can certainly solve this one what's called analytically, but we can actually make an educated guess. So yeah, educated guess, check that we're correct. So let's think about what sort of functions might solve this differential equation. So we want some function. We know that it needs to be oscillatory, so we know that it needs to be periodic. And we also need to know, we need to have some function so that when we take its derivative twice, we get the function back times by some constant. And if you think through, well, what are the periodic functions that you know? You know cosine, you know sine, you know tangent. You might go further with cotangent and things like that. But if you think about, you know stuff about differentiating sines and cosines, you might suspect that you could use maybe a sine or a cosine. And you'd be absolutely correct. What we're going to do is we're going to use a sine for no other reason than that that's the one I picked. So you could use your cosine and everything would work out exactly the same. And in fact, if you went further and you do the course on solving differential equations, you'll find that you can use them both together. But for what we're doing for today, we just want to get something simple, so we're going to use sine. So I'm proposing that this function, so this is x of t, is equal to some constant times the sine of omega t plus phi 0, solves that differential equation. And the things to notice here is that this a, my omega, and this phi 0 are constants. And why I've put in these constants is going to be clear a little bit later on. Well, let's check. So I've just claimed that this is a solution. How do we check that it works? Well, we're going to plug it into this left-hand side over here. So we're going to differentiate it twice. And hopefully, if we're correct, we should end up with minus omega squared times x. So let's check. Well, let's differentiate this once. So taking the first derivative. So this is a constant, so it just comes along from for the ride. Now I need to differentiate sine. The derivative of sine is cos. So I've got cosine of omega t plus phi 0. And then don't forget your chain rule. Need to differentiate what's going on inside here. And if I differentiate omega t plus phi 0, well, remember t is our only variable. Omega and phi 0 are constants. So I'm going to be multiplying this whole thing by just the derivative of omega t plus phi, which is just omega, because the derivative of constant times time is going to be just the constant. Okay, so that's the first derivative. I'm just going to rewrite this a little bit. I'm going to bring my omega over to this side. You'll see why in a moment. Okay, but we actually need the second derivative, so now we need to take the derivative of this again. So I'm going to take the second derivative now. So this omega times a is just a constant, so differentiating, it just comes along from the right. Now I need the derivative of cosine, which is minus sine, so I get a minus over here, get minus sine of omega t plus phi 0. And once again, chain rule says I need to differentiate this inner function with respect to time. And again, differentiating omega t plus phi 0 with respect to t, I'm just getting another omega. So if I tidy this all up, I'm bringing this omega over here. I got a minus omega squared a times sine of omega t plus phi 0. And you might look at this and go, okay, how is this helping me? But notice that a sine omega t plus phi is my displacement. That's what I was originally positing as my solution. So I can rewrite this as minus omega squared x of t. And lo and behold, this is exactly what we were trying to show was true. We wanted to show that I'd found a function x of t, which, when I take its second derivative, gives me minus omega squared times the original function. Okay, so that's nice. What has this shown us? This has shown us that we can model the displacement of our mass as a sinusoid with these characteristics. So let's talk a little bit more about the characteristics. So now it should be clear why I said that I wanted to have omega squared equal to k1 over m, because it turns out to work really nicely for our solution. But remember that our omega is related to our spring constant and the mass of our original, the mass of our spring, and the mass of our mass. Sorry, got lost with words there. Okay, so, but here's the thing, there's actually a significance here. Our constant omega, which as we've just said is our spring constant over the mass rooted, is a measure of how fast our angular frequency is changed. Well, is called the angular frequency, and it's a measure of how fast the angle changes within our sinusoid over here. It's measured in radians per second, and we'll talk about it a little bit more so that you can get more intuition for angular frequency when we talk about frequency and period. But it is a constant, and you can change what it is by either changing the nature of the spring, so changing how stiff it is or how loose it is, or by changing the mass on the end of the spring. What else have we got? Well, we have this constant A over here, and that's the maximum value our oscillation can have, because if you remember, if you just draw a straight sine graph, something like this, it has a maximum value of 1. Oops, there's a 1 and there's a minus 1. So if we want to have oscillations other than 1, then we need to multiply by something. And that something is our amplitude, and it gives us our maximum. Okay, what else have we got? So why did I add in this crazy plus phi 0? Well, the idea is that we want to be able to model any system starting at any time. We don't always want to have to start with our system at x equals 0, at t equals 0. We might like to start our system with x a little bit away from 0 at t equals 0. And this adding in our phi 0 enables us to do that. So if you have a look at this situation over here, here at time t equals 0, we're starting with our system some little way along the positive x-axis. So, because remember, this up here is x. You might not be used to that. You might be used to thinking of x in the x direction, but here we're measuring time in the x direction, and we're measuring our displacement in the y direction, but we're calling it x because we're actually measuring x in the horizontal. Sorry, physics does this sometimes. It likes to think it's logical, but it's not. Okay, so here at time t equals 0, we've got our little system. If we draw our sketch with x is equal to 0, at time t equals 0, we're probably starting somewhere here. And so we're allowing our system to oscillate out this way a bit, and then it heads back and starts its oscillation. And the whole way that we do that is by including this term in our original model up here. And if you want to be precise about it, you can work out what phi 0 should be by noting that this point over here, the difference between where you're starting at t equals 0 and where your sinusoid first goes through 0 is phi naught over omega. Wouldn't worry too much about it, but if you're interested in the details, that's what you can do. The moral of the story here is this initial phase means that we don't always have to start at x0 at t equals 0. We can start at any x that we like and still get a valid model. Okay, just a few more things that you'll hear when we're talking about oscillatory behavior. So we have a fixed period, t, and that defines the time between successive maxima, so between getting to the furthest point in either direction from the equilibrium. And in fact, it's between any two places where our displacement and our velocity repeat. So we also have, if we look at those two places, so here we have a displacement of this, and also we can see that our velocity must be the same. So that distance there is also t. So sometimes we'll talk about the period, sometimes we will talk about the angular frequency. They all get linked together. How do we do that? Well, if we think about it, we must have that the period t must correspond to a 2 pi radian increase in the sine function. So the thing to remember here is we're in radians, not degrees. So if we go from here to here, in terms of radians, we must have gone 2 pi radians. We've done a full revolution of the circle. So what do we have here? Well, if we look at what's happened, if we do a full revolution, so I'm thinking about this here, if we increase, so I'm just thinking about what's happening inside my sine function here, so I'm thinking about what is happening in my angle. So if I add a whole period to my time, so I've gone through a complete cycle, it must be the same as if I have just added 2 pi to my angle. So adding in time a complete period must be the same as adding a 2 pi worth of angle. So if we do a little bit of multiplying out and stuff, we get omega t plus omega big T plus phi naught must be equal to omega t plus phi naught plus 2 pi. And we can do a bunch of crossing out. There is our omega times our little t, omega times our little t, and our phi zeros. And so it must be that omega big T, so omega, our angular frequency, times our period must be equal to 2 pi. And this is pretty convenient because it gives us a way of getting our period from our angular frequency, which is that our period is 2 pi over our angular frequency. Okay, so this gives us the link between the two. You might be thinking, where does normal frequency, so that we measure in hertz, comes from? Well, we know that our period is 1 over our frequency, or vice versa. So if we put that over here, then we get that our frequency must be equal to our angular frequency over 2 pi. So when you're wanting to convert from angular frequency, which might not seem super kind of intuitive, to things that you are familiar with, like period and normal frequency, these are your conversions. If you want to think about what is angular frequency versus normal frequency, well, let's suppose I have one rotation or one oscillation per second. What is that? That gives us a frequency of 1 hertz. So that's one cycle. 1 cycle per second is 1 hertz. But in terms of angles that we're going through, because remember we're dealing with a sine wave here, angles we go through 2 pi. So our angular frequency says that if we do 1 rotation per second, that means we go through 2 pi radians per second. So that would give us, in 1 second, we would rotate through 2 pi radians. So our angular frequency will be equal to 2 pi radians per second. So this is just giving you kind of an intuition. So our frequency measures how many rotations we do per second. And for each of those rotations, if we're thinking about angular frequency, for each of those rotations, we do 2 pi worth of change in angle. So we multiply through by 2 pi. Okay, so those are the kind of details, mathematical details. But let's see if we can do an example. So here we've got a mass on a spring, and it's vibrating with an amplitude of 11 centimeters, with an angular frequency of 3.2 radians per second, and at time t equals 0, our displacement is 0. Okay, so what can we tell about this? Well, we're going to assume that this is simple harmonic motion that we've just discussed now. So we're going to find an equation of this form here, a sine omega t plus phi, which can describe this motion. So when we say find an equation of that form, what we're really saying is we would like to find values for a and omega and phi 0, so that at any further time we can tell what the displacement of our mass is. So please take a couple of moments and see if you can find out values for a, omega, and phi 0 based on this over here. Go on, go and do it. Pause the video, come back when you've done it. All right, let's do a quick check. So this was very straightforward. The only thing to kind of be aware of is that we use SI units. So if we have 11 centimeters, we're going to want to convert that into 0.11 meters. And we're told that that's the amplitude, so that's straightforward. We've got an amplitude of 11 centimeters, which is 0.11 meters. We're told that our angular speed is 3.2, our angular frequency, and phi 0 our phi 0 must be 0 because we know that at time t equals 0 our displacement is naught. Okay, so we end up with this equation over here, and the key thing here is what we've been trying to do all along, is now that we've got this, if you ask me for any particular time where this mass is, plug the particular time in and you can find what the x displacement is. And in fact you can do a little bit more than that, and so what I'd like you to do is think about at time 2.4 seconds, find a value for the displacement and the velocity and the acceleration. If you do that, and then I'm going to stop this video, and in the next video I'll start by giving the solutions here and then carrying on with the next bit.